Hello guys, how you doing? I hope you have a pleasant moments. This is the first session of chapter 2 of fluid mechanics, and I'm hoping to instruct you well and acquire the knowledge of this part of fluid mechanics very well. Follow me with the section. So, as I told you, this session is going to be about the first part of chapter 2 of fluid mechanics 1, which is pressure at a point. My name is Amir Reza Talaqat and my email address is amirrezatalaqat@gmail.com. I'll be delighted to answer all of your emails. It might take some minutes or several days, but I try to answer you as soon as possible. So, we are going through some principles. Guys, in order to verify a pressure at a point, let's just consider a rigid body like this. And in addition to that, it is at rest, which means there is no velocity. Putting out shear stress, two external forces are going to be exerted on this point, which are due to pressure and the weight. Weight is in this area and this direction to the downward, and the pressure is due to three different directions, which are x direction, y direction, and the z direction in the vertical. So, if we accelerate the rigid body, the question that might flashes across your mind is that will the assumption of no shear stress be valid at that action? The answer is yes, since there is no relative motion to the adjustants of a rigid body. The assumption of no shear stress is valid. The rigid body has other results than no shear stress, which is going to be illustrated in the following. So, how we can formalize the pressure at a point? If we consider a point here, the pressure might be exerted in an arbitrary angle, which is theta. If it's be exerted on this angle, as long as it is at rest and it is a rigid body, and in addition to assuming no shear stress, it is independent of direction, which is Pascal's law. So, the conclusion is that if we have a rigid body, this means that we can have assumption of no shear stress, and as a result, if we move the rigid body, the pressure is going to be independent of direction. According to Newton's law, the summation of forces on a point in each direction is like this equation, which is Py delta x delta z for this section minus Ps delta x delta s sine theta. Delta s sine theta is delta z, because if we image it on this, if we image the theta on this direction, it is going to be delta s, which is in this direction, multiplied by sine theta is delta z in vertical direction. So for sigma forces in y direction, we have py delta x delta z minus ps delta x delta s sine theta is equal to rho delta x delta y delta z divided by 2 multiplied by a y. The term here, it is divided by 2. I'm gonna illustrate it to you in following section. Don't worry about it. But if we consider the summation of forces in z direction, which is here, we have to decline the weight force either, which is gamma delta x delta y delta z divided by 2. The rest is the same, but if we want to image the delta s into y direction, we have to multiply delta s to cosine theta. If we do the calculation, we're going to reach these equations, and if we have a summation of them, we're going to reach to the fact that pz is equal to py is equal to ps, which in this area we have a py pz equal to ps. So guys, this was the end of section 2.1 of chapter 2, which was pressure at a point. I'm very happy that you have followed the video till this moment. And I'll be appreciated if you subscribe the channel in order to get the notifications of upcoming videos. See you in the next session.